Hello, and welcome to the Usefulati, the show that turns the writing of the world's most useful people into audio episodes you can listen to on your drive to work. Today we have a blog from Casey Handmer, the founder and CEO of Terraform Industries, a startup that's turning water and air into carbon-neutral natural gas with solar power. See the description for more, and let's jump in.
As recently discussed on the Carbon Copy with Brian Janus, utilities are seeing major forecasted demand growth for the first time in decades, and almost entirely from data centers. These data centers are running the internet, serving videos, hosting blogs, and so on, but most of their projected growth comes from new artificial intelligence applications, in particular through the major Silicon Valley tech companies such as Microsoft, Google, Apple, and Facebook, all of whom are looking to put gigawatts of additional data center demand on the grid. These data centers, as concentrated loads, face much the same problem as new renewable development does, being concentrated sources, inadequate grid capacity. While Janus' new company aims to improve grid utilization through upgraded sensors, there is only so far that upgrades of the existing grid can go. Sooner or later, we are going to have to break new ground to feed the beast. The challenge with grid development is that it is a permitting and construction nightmare, and like many things in the West, has gotten extremely expensive and time-consuming to execute. But the data centers need power much sooner than conventional development can build new power plants and transmission lines, even if permitting, eminent domain, technology, and construction costs were a solved problem. It is time to lift the constraint that a new data center must be attached to the grid. Instead, we can provide most of the power locally using beyond-the-grid renewable energy generation, backed up by batteries for energy storage overnight. It is fortuitous that artificial intelligence data center demand is developing in the mid-2020s, since solar and batteries have been on a 40-year cost progress curve and are now arriving at the point where this is actually possible. In a previous post, I talked about application-specific solar for synthetic fuels and for seawater desalination. Here, I unpack the economics of powering artificial intelligences with new-build solar. First, a quick refresher on solar and battery cost progress. I recently prepared these two graphs that show the learning rate for solar and batteries. The learning rate, defined as the cost decrease per doubling of production, applies to modular manufactured goods built in a factory, where process controls and innovation can result in continual improvement. For solar, this is currently running at about 44%, while for batteries it is about 23%, reflecting their relative complexity and immaturity of the manufacturing process. That said, battery production is expanding somewhat faster than solar, so both processes are seeing year-over-year cost improvements in the mid to high teens of percents. As of 2024, of course, both technologies are increasing their total addressable market at a terrifying rate and will probably continue to accelerate. Synthetic fuels, being a low-cost commodity, must minimize capital expenditure devoted to energy storage and run off pure solar during the day. Data centers, on the other hand, have relatively high fixed costs, somewhere around $50 per watt, and so profitable operation depends on achieving high utilization. I recently computed the minimum cost mix for any desired utilization and showed how these development costs will evolve over the coming decade with future declines in solar and battery costs. Note that even with today's relatively high solar and battery costs, running a 24/7 operation requires less than $4 per watt capital expenditure for power supply, less than 10% of the data center cost. Of course, there will be times that poor weather reduces battery charging, and by extension, data center uptime. This can be addressed by adding additional solar and batteries until profit declines. For example, a data center built in 2028 could have a doubly redundant solar and battery power source for about $4 per watt, which is very affordable. The trend is clear: we can get to greater than 99.9% data center utilization with relatively affordable overbuild of solar and batteries. What is this going to look like at scale? A 1 gigawatt data center, containing roughly a million H100s, would have a substantial footprint of 20,000 acres, almost all of that solar panels. The batteries for storage and data center itself would occupy only a few of those acres. This is in some sense analogous to a relatively compact city surrounded by extensive farmland to produce its food. Of course, future data centers will use more advanced and productive computers, but their power consumption and heat generation will remain much the same. Radically more efficient panels, batteries, and computers will only increase the revenue per unit land used for this purpose. The development cost of a 1 gigawatt data center would be around $60 billion, including the solar and battery power plant, and importantly the lead time and permitting complexity for each of the components: solar array, batteries, structures, racks, internet connection, and servers is about the same. This is in direct contrast to conventional on-grid power supply, whose capacity is nearly exhausted already. Is this going to pave the earth with solar? My startup Terraform Industries looks to apply solar to produce synthetic fuel, consuming substantial amounts of land, though less than agriculture, in the process. Something like 1 billion acres, or 3% of Earth's land surface area, would be sufficient to provide every man, woman, and child on Earth with United States levels of oil and gas abundance and commensurate prosperity. It is possible to imagine a future where people consume even more than that: widespread personal supersonic transport, for example, but ongoing conversion of land use away from intensive industrial agriculture toward inherently more productive solar synthetics is a clear net win for the environment. Is this the case for solar artificial general intelligence? It is currently hard to imagine NVIDIA and friends producing 100 billion or more H100s, but it is also hard to imagine our collective demand for artificial intelligence will saturate. If we are spending $60 billion on a 20,000-acre solar-powered data center development, that is about $3 million per acre. Even if the land acquisition budget is only 3% of the budget at $100,000 per acre, this is still substantially higher than essentially all land outside of major cities, including prime agricultural land. Is artificial intelligence a solar panel maximizer rather than a paperclip maximizer? Will artificial intelligences prefer to live in space instead of on the Earth? This is a tough question to answer. Today, the major external demands of data centers, power, and water are much easier to get on Earth than in space. Thousands of times easier, at least. One could imagine a fleet of artificial general intelligence satellites in sun-synchronous orbit. If they were based on the Starlink satellite bus, then the graphics processing unit substrate would cost about $10 per watt, plus launch costs of another $30 per watt or so, as approximate guesses. Substantial progress on Starship could lower this substantially, but it is hard to imagine space being cheaper to access and operate within than spare land on Earth. How much compute will we get? Earth receives about 173,000 terawatts of power from the Sun. Assuming 100% conversion efficiency, 100% coverage and application via NVIDIA H100s, 60 teraflops each, we can run 247 trillion graphics processing units for a total of 1.5 times 10 to the power of 28 floating point operations per second. Equating floating point operations per second to synaptic operations, a human brain can perform about 100 petaflops, equivalent to 1000 H100s, but consuming just 20 watts versus 700 kilowatts for the graphics processing units. With current graphics processing units, the global solar data center's compute is equivalent to roughly 150 billion humans, though if our computers can eventually match neural efficiency, we could support more like 5 quadrillion artificial intelligence souls. It seems that artificial general intelligence will create an irresistibly strong economic forcing function to pave the entire world with solar panels, including the oceans. We should probably think about how we want this to play out. At current rates of progress, we have about 20 years before paving is complete. If economic returns to artificial intelligence continue on current trends, use of any land by solar-powered artificial intelligence will return roughly 100 times more than agriculture, which creates a strong economic forcing function for the conversion of farms to solar arrays, initially providing humanity with incredible economic productivity and wealth creation, and ultimately displacing the land humans need for food. While it is possible to produce more food on less land, in particular by using solar photovoltaic to power synthetic food generation, humans are already positioned to lose out to artificial intelligence on the neural cycles per acre of land used metric. Graphics processing units consume much more power per floating point operation per second, but solar panels produce much more power per unit acre, balancing out this drawback. If humans want to eat food grown on the Earth in future, they will have to increase economic productivity enough to offset the greatly increased cost of food caused by land use competition by artificial intelligence. We have achieved roughly a 100 times increase in gross domestic product per capita since the beginning of the Industrial Revolution 300 years ago. Now we have about 20 more years to achieve another 100 times increase. Go!